Our next speaker is Andrew Duncan from Electromagnetic Imaging Technologies.
Good morning to you all. It's an absolute pleasure to be here, and many thanks to DMEC for the invitation. In this presentation, I wanted to review some of the developments in EM survey technology from the last decade, but I find it very hard to pack that into a 20-minute talk. So this is going to be what I consider to be rather brief and really missing perhaps some important examples. So there will be some examples towards the end of the talk of data sets that talk to some of the issues I'm going to discuss about technology development, but this won't be a comprehensive set of examples by any means. I'll be talking about transmitters, receivers and sensors, but not a comprehensive list of all developments. And I'm going to talk about TEM exploration for highly conductive mineral deposits, because these type of targets are drivers for technology development in TEM. You got a laser pointer? And at the end I'll summarise what I believe to be the most important directions for the future. Information has come from my peers in the industry, and my own observations, and the paper that is published as part of this convention does have a little bit more detail, and along with the references that will be useful to cite if you're interested. Let's start with transmitters, and it may be no surprise to most of you that the trends that were going on 10 years ago have continued, and that is that there's been an increase in the power of transmitters that are used in time domain EM, especially in areas with in terrain that has good access. That's a little bit more difficult in areas without good access. And there has continued to be a decrease in the typical frequency of operation of TEM transmitters, and that's resulted, I think, from a combination of a couple of things. An increasing recognition of the utility of fairly low frequency EM measurements, and a range of sensors that have good performance at those low frequencies, and those are driving TEM surveys to have improved discrimination and detectability of good conductors. Some examples of transmitter developments. This is the picture on the right here is a 70 kilowatt transmitter system parked at a nickel mine in Western Australia. This is a system built up by GAP Geopack in Australia, called a HPTX70. You can see that's got some serious current capabilities, up to 350 amps, and a maximum power of 70 kilowatts. Now that's sitting on a dual axle trailer. And that weighs roughly 3 tonnes, I believe. It is easy to pull around with a four-wheel drive. There's been considerable development effort applied to the very important issue of safety, and automation, which feeds back to safety as well, and ventilation, of course, because that thing is generating a lot of heat, and it is able to operate at high temperatures. It's usually used with fairly big wire, as I've noted there, and that is pretty big wire compared with what might have been standard 10 years ago. An example from Yves Lamontagne's system is UTEM system. This is a more portable system, and the UTEM 5 is capable of operating from 2.5 kilowatts to 12 kilowatts with a very impressive dynamic current waveform regulation to 0.01%. UTEM 5 is always operated as a 100% duty cycle system, and some facts and figures there on the UTEM 5 transmitter capabilities, up to 18 amps RMS into a 1,000 metre square loop, and typically with 14 gauge copper wire. The waveform is designed to be easily deconvolved to an effective square wave. Some general comments about transmitter productivity. And some receiver equipment, and for example, UTEM systems and smart TEM systems have the capability to separate simultaneous transmitter waveforms. So in other words, multiple transmitters running simultaneously into different loops the receivers are capable of separating those two signals out into effectively two different surveys going on simultaneously. Another thing that you could do is run multiple loops in an automated sequence fashion from a single transmitter using what is effectively a multiplexer here, which takes as an input the high voltage output from a single transmitter and multiplexes that out under a fairly automated control to multiple loops, in this case up to 4 loops. Another bit of gear that seems to be getting used more often in EM surveys is a current monitor. Moving on to sensors now, and we always talk about the signal to noise of a sensor, and that's an integral part of improving the quality of TEM data. Increasing the performance of a sensor can happen a number of ways, and the most obvious way is by reducing the noise level of a sensor without reducing the noise level without reducing its sensitivity. We could consider increasing the bandwidth of a sensor without increasing its noise level, or we could make the sensor easier to calibrate or easier to use. And there are logistical issues tied up in this as well. It might be useful to make it less responsive to external effects like wind and vibration. And we often see pictures like this. This is an example from, I think this is an example from a Jim McNay presentation where we plot the intrinsic noise of a sensor in units of nanotesla per root hertz or picotesla per root hertz as a function of frequency. We've got a range of EM sensor types, fluxgates, induction magnetometers and SQUIDs represented on that graph. SQUID magnetometers, these systems were around 1 decade ago, but they've improved in performance. They have superconducting elements, so they require a cryostat with liquid nitrogen or liquid helium. There are several manufacturers. I've got a couple listed there: IPHT in Jena in Germany and CSIRO in Australia have manufactured SQUID systems for mineral exploration. And usually the sensitivity of these systems requires that they use shielding from the wind when they're operated in the field. Fluxgate magnetometers are fairly ubiquitous in mineral exploration TEM. They're small, low power, relatively expensive. They are at the noisy end of the spectrum. They're at the top of that last curve that I showed you. And the bandwidth of these sensors is generally low. However, they are simple and very popular, and as a result, they've been responsible for billions of dollars of metalliferous discoveries in the last couple of decades. That was a picture of one down a hole there. Atomic magnetometers, not routinely used in AC measurements at these sort of frequencies that we talk about with TEM, but they can be easily configured to make a scalar measurement of the magnetic field at EM type frequencies. A general comment about the performance of these systems over the last decade, that the sensor intrinsic noise that we see, for example, in a cesium vapor magnetometer hasn't improved much in the last decade. But I do see potential for these type of systems to improve a fair bit in the future, and the electronics that marries with these systems has improved a bit over the last decade. Inductive magnetometers, I think there's a lot of potential. These are not a new type of sensor, but I suspect that the uptake of inductive magnetometers in commercial EM surveys in the next decade will be significant. As I pointed out there, they've been used historically for MT, CSAMT, but there are a number of TEM systems that have historically used inductive magnetometers, and they're commonly used in 100% duty cycle TEM measurements. A couple of examples of inductive mags there. On the left, the new UTEM 5 3-component inductive magnetometer sensor from Lamilton Geophysics. On the right, a couple of ARMIT sensors from RMIT/Abitibi. Moving on to receiver systems, and the areas where we do see some significant improvement in performance in the last decade really relate to time series measurement and processing. GPS synchronization, which has been around for some time, but the uptake on that is now more. And as you can imagine, with the evolution of electronics, things like better battery life, better screens, electronics reliability, and higher channel counts are now rather more ubiquitous than they were 10 years ago. Example of a receiver development from the last 10 years, this is SmartTIM 24. System 16 channel, 24-bit. It has an integrated, you'll notice there that there's a commercial PC completely integrated into that system. And this particular receiver system is used with transmitters and sensors of convenience. For example, most of the commercial transmitter and sensor systems that are out there today can be integrated with this. Has GPS synchronization. Talked about batteries before, and this is a full time series recording. Now, of course, there's a hard disk in there, and it's streaming raw data on up to 16 channels. Another example, the Lalor Physics UTEM 5. This is another recent development, even more recent. So 2011. It has new features over the previous generation of UTEM receiver. It has a fibre optic sensor interface, so the sensors typically married to this system are digital. And there's a facilitation here of the type of technique I mentioned before with multiple interleaved transmitter frequencies. So in other words, simultaneous transmitter frequencies. All that facilitation is built into this instrument. Eve points out that there are new options for stacking and windowing filters with this system, and time series treatment and oscilloscope type viewing of data sets. It's used almost exclusively with 100% duty cycle operation, and it's also used for other techniques such as inductive source resistivity. Another example of recent developments. This is a system called Volterra from SJ Geophysics in Vancouver. This is a truly distributed EM data system, or capable of doing other techniques as well, but used for EM. So it has a fast enough sampling setup for EM. It's normally interfaced with inductive magnetometers and normally used at 100% duty cycle. They're small and light and include GPS synchronization. And on these systems, data is harvested and processing is done after acquisition. Borehole TEM systems, the same sort of things are driving borehole systems. So they're coupled with higher power transmitter systems. They're typically used with high resolution stream samples and time series recording, etc. The UTEM 4 borehole system, there's a bit of a description there. I won't go right through that. It's a very innovative borehole system. It's an evolution of borehole technology that's been at Lalor Geophysics for some time, and there's plenty of improvements in the electronics and software going on there. DigiAtlantis is a three-component borehole Fluxgate Magnetometer system that was born in 2009. It's evolved from an analog version that started in 2004. It has digital streaming of data over copper wires, and it's used with transmitters of convenience. It's usually employed in 50% duty cycle surveys and often used in MMR surveys and other types of borehole systems. Autonomous borehole systems, there are two examples I'm citing here. That the Volterra system that I mentioned with regard to ground EM be used in the borehole with a three-component Fluxgate magnetometer. And Voisey, with Ben Polzer in particular, developed an in-house borehole TEM system called UTEM. Both of these systems record raw time series for subsequent processing, and both of them are completely disconnected from the surface and don't require any kind of an electrical connection at all between surface and probe. Okay, I'm going to just talk briefly about highly conductive targets, because these do drive TEM instrumentation development. Targets are typically in the category of a big nickel copper sulfide deposit. We hear the terminology superconductor used. They are difficult to see in an off-time measurement because secondary currents flow virtually in phase with transmitter currents. I'm just going to present some brief model results from a simple but accurate modelling scheme for a thick disk in a TEM survey. I'm just going to use a circular transmitter loop and a cylindrical disk target. It's perfectly adequate for exploring the behaviour of highly conductive targets. And I'm modelling with non-magnetic materials here. Right, that's the model on the left. I'm going to show you some results from a model of a 1,000 metre diameter transmitter loop at the surface carrying 20 amps. The targets are going to be horizontal disks of variable thickness at 1,000 metres depth of various thicknesses and conductivities. I'm going to show the results from 200 metres off hole, effectively simulating the vertical component measurement off hole 200 metres away from that target. I'm going to show you on time 50%, off time 50%, 100% data, and 100% duty cycle data with the last on time window subtracted. A couple of models here. One of a 100,000 Siemens target and a 1 million Siemens target. So both have a conductivity of 100,000 Siemens per metre, times 1 metre in this case, times 10 metres in this case. These are 400 metre diameter discs. The four quantities that I mentioned before here, 50% duty cycle on, 50% off, 100% duty cycle, and late time normalised 100% or late time corrected 100% duty cycle are shown here in these four colours. I'm only showing the results from 0.1 Hertz and 10 Hertz. This is the decay, time, and amplitude. I'm plotting this as a negative decay using the convention that an off-hole anomaly is a negative. You'll notice as you go to a much higher conductance target, the off time results and the late time normalised 100% duty cycle results start to depress. But these are far from being non-decaying decays at 0.1 Hertz. Going to 0.1 Hertz for an EM survey in a highly conductive environment makes an enormous difference. So I'm plotting 0.1 Hertz versus 10 Hertz, where there's really not much decay happening at 10 Hertz. There's very little response in the off time at 10 Hertz. It's quite a different story at 0.1 Hertz. I'm going to quickly show you the results of a Voisey's Bay ovoid model. This is also buried at 1,000 metres, which is not the depth of Voisey's Bay. It's quite a shallow deposit. And these extreme examples do exist. This is effectively a 10 million Siemens body. On the right, I'm showing you what the currents in that body look like in a vertical slice through the middle of a disc, look like after 5 seconds of decay in a 100% duty cycle survey. They're sitting right on the edges. And these are the decays for that. It's important to note that the currents are sitting right on the edge. Now, if you model this by taking 95% of the volume of this highly conductive material out of the middle, in other words, just leaving a 5 metre shell around the outside, the TEM results are almost identical. So the currents are really just sitting on the outside of these things. A couple of results that flow on from that. Increasing the thickness of a tabular conductor doesn't necessarily change the TEM behaviour significantly. Certainly increasing the long dimensions of the conductor does. I haven't really shown that in the presentation, but I thought it was important to say. 50% duty cycle on time and 100% duty cycle on time results are similar. Late time response for 50% duty cycle off time and the late time corrected 100% on time are virtually identical. Come on. Oh. A couple of examples now. This is going to be very quick. I'm going to show, this is a surface example using a scalar field measurement, so a cesium vapor magnetometer carried out by GAT Geophysics. This is using the high-powered transmitter we looked at before. There's a 1 kilometre loop here. For a very shallow target, this is a test target. That's why we're using a big loop with a test target. There's only 40 stacks, 5 minutes, 40 stacks, 2 repeats, 5 minutes per station. in this example. I'm going to show you all the decays for this line across this little target. All the decays there, that's from one line. So there are 2 decays from each station, multiplied by a dozen or so stations in the line. The important thing to note is the repeatability at late time here is less than 0.5 picotelesla. It's less than 5 femtoteslas per amp when you normalise by current. Near the wire, and there are stations 50 metres from the wire, the secondary field precision is roughly 1 part in 1 million of the primary field. We've heard a bit about the Lalor VMS deposit in the last decade. It was discovered right before exploration 07. It's a beautiful EM target, and I just posted this profile of Borehole EM data at 0.5 hertz, just to show a nice example of a Borehole EM in a nice conductive VMS. An example from Western Australia of a nickel discovery. This was a discovery for Borehole EM. The paper there that outlines the details of the discovery there. It was discovered in this decade. And some examples of the data. This is not from the discovery hole, but it's from a hole that passes 20 metres away from this body. And this is in the paper, and you're welcome to consult that. There's $600 million worth of nickel sitting in that at the time of at the nickel price at the time of discovery. And there's some general comments there about the nature of the on-time and off-time data. I'm going to skip through that. Now, summing up, ground and borehole TEM surveys, there's no doubt they're a hugely important tool in metals exploration, and they are responsible for generating significant discoveries. I firmly believe that the evolution of sensors and all the other parts of EM systems, all the other parts that go into a TEM survey, and the usability of all those things is going to keep going in the next decade. And I've got no doubt that distributed EM systems are going to become popular in the TEM survey industry in the next decade. And that's also going to rely on the presence of cheap, abundant, good EM sensors that we can hook up to a distributed system. My acknowledgements, and that's all, Glenn.